In this video, we are going to present a new attack on the OAuth 2 authorization framework, which is called browser swapping. The OpenID Connect identity layer on top of OAuth 2, which is often used for single sign-on solutions, is affected as well. SySS discovered this attack in a penetration test of a web application and is currently working on a standardized solution with the Internet Engineering Task Force. Let's start with a quick demo of a fictional web application. On the left you can see the attackers, and on the right the victim's web browser. The attacker's web browser already shows our demo web application with a login button. When clicking the login button, the attacker would be redirected to the authorization server, which in our setup is a Keycloak installation. Now the attacker copies the authentication URL of the login button and sends it to the victim under a pretext to browse it. In our demo, the attacker starts a conversation with the victim using a chat application. When browsing the URL and logging in, the user will be redirected back to the callback URI of the application. However, because this authentication process was requested in the attacker's context, the application denies the user access. Most users complain to the attacker that the link is not working. The attacker pretends to help and asks the user for the link of the error page. When browsing this link in the attacker's web browser session, it works. The attacker is then successfully logged into the application with the victim's account. Let's explain how this attack works. By clicking the login button, the web application generates a random state parameter and remembers it within the attacker's session. The web application adds this state parameter to the authentication URL, to which the new web application redirects the attacker at the authorization server. After authenticating the user, the authorization server reflects the state parameter in the callback URI, which redirects the user back to the web application. Within the user session, the web application fails the comparison of the remembered state parameter with the attacker's state parameter from the callback URI. This state verification should actually serve as a protection mechanism against cross-site request forgery attacks, where attackers try to log in users with their own account. The client therefore rejects the user's authorization code, which remains unused in the URL bar until the user shares the entire callback URI with the attacker. When browsing the callback URI in the attacker session, the state verification succeeds, and the web application resolves the provided authorization code for an access token. Since this authorization code was issued to the user, the attacker will be logged into the web application as the user. Let's have a look at the mitigation strategies. The OAuth 2 standard already comes up with a strategy to mitigate the URL sharing component of the attack. Therefore, the web application must redirect the user's browser from the callback URI to a dedicated error message, which does not contain any secrets like the authorization code. In our example application, it would look like this. However, this is often forgotten by developers because of poor error handling. In specific scenarios, attackers may access these unused authorization codes anyways. One example might be a low-privileged auditor with server log access only. Such a log auditor can perform a browser swapping attack against higher privileged administrators to access their unused authorization codes in the server logs to take over an administrator session and elevate the own privileges. SySS also found a trick to turn most of these less critical log access attacks into critical URL sharing attacks. For this, attackers append the response mode parameter to the authentication URL, which will be sent to the victim, and set this parameter to fragment. After the user authentication, the authorization server forwards the victim back to the callback URI. Because the response mode was changed to fragment, the state and the authorization code are contained as fragment parameters instead of query parameters. Since the web application does not expect these parameters in the fragment part of the callback URI, the login within the victim's browser will fail too. Clearing the user's URL bar from secrets also fails, because browsers persist the fragment part of a URL across redirects. The attacker can therefore proceed the attack by pretending to help the victim to make them share the error URL containing the authorization code. The attacker then only needs to insert the fragment parameters of the error URL as query parameters into the callback URI. Currently, there is no standardized solution to completely mitigate browser swapping attacks. Therefore, SySS can only suggest mitigation options. Whether these options apply for your application depends on the exact implementation. SySS recommends verifying the effectiveness of applied solutions by security experts. In a first place, clients must mitigate attacks based on URL sharing to increase the attack complexity. Therefore, clients must sufficiently remove all secrets from the callback URI. This is especially important for error cases where the authorization code has not been resolved for an access token yet. To do this, SySS highly recommends to forward the user from the callback URI to a success or error page with a trailing hashtag. This makes the browser clear the fragment part of the URL after the redirect. If you are affected by the response mode mutation, restrict the response mode of your authorization server's OAuth client configuration to allow only the client's expected response mode. Attackers may access unused authorization codes which have been transferred as query parameters in various ways. Mitigating all of them requires high effort. As an alternative, applications might use different response modes than query. Server-side applications, such as our web application presented here, might use the response mode form post, where the authorization code is transferred as a post parameter. Post parameters are known to contain secrets and are therefore typically not locked. Client-side applications, such as JavaScript-based single-page applications or native apps, might use the response mode fragment. In both cases, make sure that you can enforce the used response mode at the authorization server to mitigate response mode mutations as well. In case of a mismatching state, the client intentionally ignores the authorization code, which will therefore remain valid until the attacker uses it. While it is standardized for tokens, no standardized invalidation process officially exists for authorization codes. Depending on the implementation, sending an invalid token request with a valid authorization code might serve as well if the authorization server invalidates the authorization code then. While invalidating tokens could provide a means of mitigation against browser swapping attacks, there are additional problems associated with this measure. When the client redirect URI is not reachable, the client never gets the authorization code and can therefore not invalidate it. This is feasible through a number of different ways, which are currently under discussion with the OAuth Working Group on the IETF. SySS has sent IT security consultant Jonas Primbs to the recent IETF meeting 124 in Montreal. Right now, SySS is working together with the OAuth Working Group of the IETF on a standardized solution to fix browser swapping. SySS recommends all authorization server providers and application developers to apply the recommendations suggested on the previous slide and to stay informed on the latest updates. You want us to hack you? Just contact us.